Okay, so we have our 4 countries that are listed here, and we know the amount of different types of food they have in each one. And the question is, which one's the odd one out? You did it on Friday. Maybe you remember the answer. Everyone got it on Friday, which was, it was the second column. That's exactly correct. Okay, we didn't get into it last time, but now let's get into it. How did you tell it was the second column and not the other ones? Why is the second column the other one now? How did you select? So, I guess, how many people voted for second column? 14 out of 17 people voted for second column. Why did you choose second column, you 14 people? Yeah.
For me, it kind of keyed off the differences in fresh fruit and fresh potatoes.
Yeah, okay, so you said, I was looking through them, and there's a lot of data, too much to handle in my brain, so I just looked at fresh fruit and fresh potato. And then in those two, why is column 2 the odd one out? Oh, okay, yeah. Well, you tell me, what did you see?
They're kind of flipped.
They're flipped, yes. So all the other ones, they have more fresh fruit and less fresh potato, right? 956, 566, 1,000 something, 800. But those are, column 2 is flipped. So they kind of have the ratio of potatoes to fruit. They have more potato than fruit. Everybody else has more fruit than potato. Yes, that's a very good way to do it. And I think that is the way I would sort of do it. I will say, okay, this is a great example of what you actually just did. You did dimension reduction. You had 17-dimensional data, and you reduced it down to 2 dimensions by a very classic, time-honored method of ignore some of the dimensions. So you took some of the dimensions, you threw them in the trash. You said, of these 17, let's throw away 15 of them, and we get down to 2 dimensions. What we are learning is this PCA stuff. It is also dimension reduction, but it's kind of trying to be a more sophisticated way. So instead of saying, just delete, like find the most important one, or delete all the other ones, we're trying to find combinations of more than one thing together that will tell us the differences. So it's a great way to do it. I absolutely agree with you. Did anybody do something different, or did anybody look at a different row other than those two? Yeah.
Yeah, just most of the columns, they're like within, I don't know, 25% of each other, except for like alcohol and drinks as well, where column 2 has like a third of everybody else.
Yes, okay, this is another one. So yeah, so you're saying a lot of them are quite similar, and again, when they're quite similar and you're trying to tell them apart, probably you should just ignore it, right? Like, 198 versus 187, like, I don't know, those are too close for me to tell. So when they're really close together, we just ignore it. And then this is another row where you can see some differences is in alcoholic drinks. And again, the second one is the odd one out. So you're all exactly correct. And again, what we're going to try to do is try to come up with a more sophisticated way where instead of ignoring the little differences, like in processed potatoes, it was a little bit less than the other ones. Instead of just ignoring the little differences, we're going to try to stack up these little differences into some smart way to combine everything into one new column that tells us the difference. And in fact, this has been done for us. This is an example from a nice page on principal component analysis, which we're learning. You might notice the very first thing they have is this 2D example, which looks just like what we did in class. Let me move this chair out of my way. Yesterday, so you have a bunch of points, and the principal component is kind of the direction in which these points are the most spread out. You want them to be the most spread out because that way you kind of preserve as much information as possible. And over here are the original points, and then here is what happens after you project them. The 2 coordinates are called PC1 and PC2, the first principal component and the second principal component. Last class we talked about how to get the first principal component. You find this one special direction that maximizes the difference. In 2 dimensions, PC2 is everything that's left over. So after you've chosen this red direction to be PC1, which is indicated over here with this little red and green ruler, then the other direction has to be the green direction. And the fun thing about this thing is it's interactive, so you can slide the points around and see how things change. So if you make your points go all wonky like that, now the principal direction is this way, right? So this way, and now they look like this. So it's always going to be in 2 dimensions in some kind of rotation of space, so that the direction where they're all spread out is the PC1, and then everything else is the PC2. And so again, this is the reason this is nice is because it automatically, given your data set of points, it automatically finds this direction in which most of the variation happens. Maybe you can even delete PC2 and only look at the PC1 and get most of what you need. So it's a method of data reduction. It really starts to get powerful, not in 2 dimensions, but in higher dimensions, like the example we're looking at. Here's 3D. We'll do the 3D one in a minute, but here is the one we just did, where I took the thing from. And this is called the eating in the UK. What if our data has more than 3 dimensions, like 17 dimensionals? This is the table is the average consumption of 17 types of food in grams per person per week for every country in the UK. For every country in the UK. Wait, I thought the UK was just one country. Why is it, wait? Every country in the UK. Every country in the UK. Well, the UK is the United Kingdom, is actually made of 4 countries. Here are the 4 countries. There's England, Northern Ireland, Scotland, and Wales. Those are the 4 countries in the UK. The way you know that there are 4 countries is they all have different teams in the World Cup. That's how you know. So England has a team, Scotland has a different team, and Wales has yet another team. And because they're different teams, they're different countries. This is a somewhat confusing thing that the UK is kind of like a country, but each of these individual things is also kind of like a country. It's kind of like provinces in Canada, although a little bit more muddled. So hard to understand, but you have these 4 countries. And that's why it's called the United Kingdom. I think a long, long time ago, these were like independent like kingdoms, and then there was like some king that came over and conquered everybody, and that was the United Kingdom, the UK. That's my geography lesson for the day. Wait, actually no, that's my history lesson. The geography lesson is coming soon. The table shows some interesting variation across the different types of foods. Hard to see what they are, but you guys figured out by staring at it for long enough that Northern Ireland, the second column, is a little bit different than the other ones. Northern Ireland is a little bit different. We could have also done it with PCA. So PCA would have said, take these points in 17-dimensional space and find the direction along which these points are the most spread out. So again, thinking of the analogy in 2D, imagine there were 4 points, the 4 countries. Find the direction in which they're the most spread out, and then rotate so that we're looking in that direction, and then look at the data. And in 17 dimensions, this is quite a big reduction. So well, we will get back to that one. It looks like this. So you find the direction in which they all vary. Again, these things kind of go together, right? People, like, the ratio of how much soft drinks to other things people drink in different countries will be approximately the same in all the countries. It's just very small differences. So kind of all of these things point mostly in the same direction. It's the small differences that are different. But when you project it down to 1 dimension, it looks like this. So you have this PC1, which is some linear combination of the columns at some direction in 17-dimensional space, along which those 4 countries are the most spread out, and you get this nice thing. So Northern Ireland is way, way, way over here. Scotland, England, and Wales are all over here. So you can very clearly see, in 17 dimensionals it's hard to see, but in 1 dimension it is completely obvious to see which country is the odd one out. These 3 are similar, this one is the odd one out. So it's very, very easy to see in 1 dimension. So this is one use of this thing. You take 17-dimensional data where it's hard to see things, you reduce it down to 1 dimension, and sometimes you can get what you want out of that. Now we need the geography lesson. Does anyone know why Northern Ireland is the odd one out? This is, if you don't know geography, then you won't be able to answer it. This is a geography question.
Is it a separate island?
It's a separate island, that's right. Wales, England, and Scotland are all on 1 island. The name of that island, you would think the name of the island would be the United Kingdom Island. It is not. The name of the island is Great Britain. Great Britain. Okay, let's get a map. Map of Great Britain. Map of Great Britain. Okay, this is a beautiful, beautiful little map over here. Okay, so this big island over here is called Great Britain, and Great Britain is split up into 3 parts: England, Scotland, and Wales. Like we said, the 3 countries. But there is another part of the United Kingdom, this little guy over here, not on Great Britain, on its own island, called Northern Ireland. I believe the name of the island that Northern Ireland is on is called Ireland. Don't get mixed up though, because Ireland is a different country. Geography is more confusing than math, if you ask me. Okay, but the point of the story is that not like our data figured this out, right? Inside our data was the fact that these 3 are related, and this one is the odd one out. We sort of figured out the geography just based on our 17-dimensional data. Okay, I think that's all I wanted to say about that example. This is going to lead us into more things, but this is the first example of a real-life use of this. I think it's nice and clear. You can automatically tell differences in data by doing this PCA quite easily. So it's a really useful tool in your toolbox. Any questions about this? Okay, the next thing we're going to do is ask, okay, there's one direction, but you can do more than one direction. So you don't have to always reduce down to one direction. You can reduce down from 17, instead of reducing 17 to 1, you could do 17 to 2. Okay? So you could do 17 to 2, and it would look like this. So now you see that, okay, Wales, England, and Scotland, they're all kind of similar, and Northern Ireland is different. But Scotland and Wales are actually very different in the other direction. And this is the second principal component direction. How did we get this? And this is mathematically what I want to briefly talk about here. Is last class we saw how to get the first principal component direction. In this class, I want to talk about how to get the second principal component direction and higher ones. That would be this. Okay. Okay. So the first principal component. This was last class. Direction. It is the direction that maximizes the spread out. Direction maximizes the spread of points. That is what we did. We were maximizing the sum of the squares of the spread of the points. Maybe I should say the spread of the projected points. So we were projecting, and then we were maximizing the spread. Let me remind you with a picture what this was like. So we were saying, what direction is the best? Well, the direction that is the best, we can try all the directions, and we want to make the sum of the squares of the points as high as possible. And so you pick a direction where these projected points, when you project perpendicularly from a data point onto this line, where they are spread out as much as possible. And we figured out it was something, in this example, it was something like this. Something like that, the sum of squares is as high as possible. That was the first principal component direction. What about the other principal component directions? PC2, PC3, and so on. This is a kind of a recursive algorithm. You can replace the data with its, I'm going to do this buzzword, orthogonal projection. Orthogonal projection after PC1 is removed. So in other words, we have our original data set, which is n dimensional. And we are replacing it with a kind of a new data set, which is going to have one dimension. This is the PC1, the principal component number 1. And then we're going to have n minus 1 dimensions, which is what you get, which is perpendicular. What is left over? Left over after the projection onto PC1. If you had a nice linear algebra class, you'll recognize this. This is a change of variables. There is a process called the Gram-Schmidt process that this is related to. This is also known as Gram-Schmidt. That is related to this kind of thing. But if you've never heard that, don't worry about Gram-Schmidt. Gram was some guy, and Schmidt was some other guy. So it's not like a gram, like a kilogram. It's some dude named Gram. Anyway, you transform your n-dimensional data into one dimension and everything left over. And I can show you in a picture what this looks like, because it was literally the picture we were just looking at. Where did my picture go? Here it is. So this green point that I've labeled here as original data, I projected it onto the blue. So I converted this blue point into this blue vector over here. What is left over? It's also on the board. So the projection is this vector from 0, 0 to the projected data, this blue line. What is left over after that? Well, it's that little green line. So instead of writing the point as in the x and y coordinates, we write it in the blue and the perpendicular direction, the green. So let me write that down in 2D. Example, when n equals 2, we have this nice axis. We have some point over here, which is described by its x and y coordinate. So you say x plus y. And we replace that with some new direction. So we say, let's do this nice blue line. And we will write, instead of writing the original vector v as some amount of x plus some amount of y, we could instead write it as some amount of blue plus some amount of green. Let's call that and the blue was PC1. So that's equal to PC1 plus, and then this green thing is perpendicular to PC1. So I'm going to call that PC1 perp. PC1 perp. And this little sign means perp, or perpendicular. And so this is PC1 perp. It's everything that is left over after you have projected onto PC1. And by the way projections work, it is perpendicular. So this is like a fundamental theorem in linear algebra. You could rewrite the same vector in many different ways. You can write it in terms of the x and y as some amount of x plus some amount of y. Or you can write it as some amount of PC1 plus whatever is left over. And in general, this PC1, because it is a line, this is always one-dimensional. And this perpendicular thing is always n minus 1 dimensional. Okay. That's because the total dimension has to be n, and that's when this thing is n-dimensional. In this example, n equals 2, so this is also one-dimensional. So it's kind of easy to see. Let's do the same kind of picture in 3 dimensions and see what that would look like. In 3 dimensions, I guess I have to do it down here. Example when n equals 3. So now you have to imagine, and the drawing is going to be much worse than it was before. Here is the 3-dimensional space. Okay, here it is, 3-dimensional space. Here is a point in 3-dimensional space. The point has an x, it has a y, and it has a z component, right? And so any vector v can be written as its x component plus its y component plus its z component. And now, when I have some line in space, the principal component that we found before, maximizing the spread, I guess let me do it in the same color as before. In blue, it's some direction over here, PC1. And you can write this as the PC1 plus what is perpendicular to PC1 in this case? In this case, there's a whole plane. So you have to imagine some vector coming out of the board. And there's a whole plane that this thing slices. And this plane lives in space. So there's some big plane like this. I guess I drew it in green before. So now there is a plane. It's all the things that are perpendicular to this vector. So I'm drawing all these perpendicular directions to help you imagine this perpendicular plane. Okay, and it looks like this. Some big plane over here. Okay? So then when you take a vector in the perpendicular space to PC1, it's a 2-dimensional vector. It lives in this plane. So this is some vector in PC2, or PC1 perp, rather. PC1 perp. And this is now 2-dimensional in this example because it's a plane, and this thing is 1-dimensional. Okay, and this works in general. It's always 1-dimensional is the line, the PC1, the line you projected, and then the leftover dimensions, all the other stuff is n minus 1 dimensional. And this is effectively its change of variables, where something we used to describe it in n-dimensional space using the coordinates, using x, y, z, etc. X, y, z, dot, 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 the original things. And we have transformed it into PC1, which is some linear combination that maximizes the spread. So the new linear combination is PC1 vector is some linear combination. It's like a times x plus b times y plus c times z, dot, dot, dot. It's the combination that maximizes the spread. And then everything else, these are things that are all the directions perpendicular. All directions perpendicular to PC1. Okay. So very nice. So last class, I kind of tried to describe how we find this PC1, and I didn't worry about the other stuff. And now I'm saying, as soon as you find PC1, you can think of the leftovers as being some vector in n minus 1 dimensional space. In the example that we did with the countries, the geography and history lesson, let me see if I can find the geography and history lesson yet again, or if it is gone forever. Oh no, whatever will they eat in Northern Ireland? Okay. Here? Okay, great. So, right, so this was 17-dimensional space. So every country was described by a 17-dimensional vector. And then I said, we find this one dimension that describes them as much as possible. And if you subtracted this vector from that, you would be left with vectors that live in a 16-dimensional space. That is the kind of leftovers. Okay, that's where we are so far. Is this idea of a perp space more or less is the picture? This is a pretty horrible picture. If you showed someone this picture, they would be like, "What are you doing, man?" Yeah, My 6-year-old draws better pictures than this, but hopefully while I drew it, the story was clear. Any questions or comments about this perp space? Who's seen this perpendicular thing before in linear algebra class? Who has never seen perpendicular things in linear algebra class? Okay, so maybe I'll do a little reminder. The perpendicular equals perpendicular equals at 90 degrees to each other. And it's related to the inner product, right? With the inner product in linear algebra. Remember, the x and the y is the inner product. Let's see, who's seen an inner product before, or a dot product? Some people write this as x dot y. Who has seen a dot product before? Okay, lots of people have seen dot product. If you've seen a dot product, the thing that you probably have seen perpendicular, you don't remember the notation. Perpendicular, x and y are perpendicular. That means that is the exact same sentence as the dot product of x and y are something nice. X, y, or x dot y equals, where it's a very specific value that goes here. They're perpendicular if and only if their dot product is what? Someone said it just now. 0, exactly, yes. So if their dot product is 0, that means they are perpendicular. So all of this stuff is to do with dot products and things like that. If you've never seen perpendicular, we're talking about finding the set of points where the dot product is 0. If you want to think about this in terms of equations, someone says, I'm thinking of all the points that have dot product 0. That is saying I have n parameters, because we're working in n-dimensional space, but I have one equation. So how many solutions are there? There's an n-1 dimension of equations. So maybe that's worth writing down. So the set of points perpendicular to PC1, that is some set. This, you could write this as the set of all vectors v, where the inner product with v and PC1 equals 0. This is one equation, and this is vectors in n-dimensional space. So you have n unknowns. So what is the dimension of the space where you have n unknowns and with one equation? It is n-1 dimensional space. So this is why this is PC1 perp, and this is n-1 dimensional space. This is like trying to jog your memory from linear algebra class, but of course, maybe you didn't have a good linear algebra class. Dimensional space, in which case you're missing out on the linear algebra. Okay, this is vaguely more detail than I wanted to say, but okay. All right. Any other questions or comments about this perpendicular space? Why is this such a big deal? Maybe we can take the original data set and peel off one dimension and have n-1 dimensions left over. Well, that's not exactly what I wanted. I wanted to do PC2, right? In the picture, they said you have PC1, and then you have PC1 and PC2. How do we get PC2? You haven't told me how to get PC2. You said you do PC1 plus 16 other dimensions. Oh my goodness gracious. How do we get PC2? This is the next question. So we have this decomposition, but how do we get PC2? How do we get PC2? What is PC2? Does anyone want to take a guess? You have this decomposition. You have PC1 plus the 16 other dimensions. How do you get PC2? What would you do? Yeah, you want to take a guess?
Should explain the values again.
Again, yeah, you just do it again. So you take your 16 other dimensions and you say, pretend this is a new problem. I now have 16 dimensional space. In what direction of these 16 leftover dimensions does the data vary the most? So the answer is, do it again on the leftovers. Do it again on the leftover n-1 dimensions. So the PC2 is the direction in which anything perpendicular to PC1 is spread out the most. Anything left over from PC1 is spread out the most. So you've already sort of extracted the direction in which you have the most amount of variation. Once you remove that direction, you have left 16 leftover dimensions. PC2 is like, of the leftovers, how much is left? which direction would vary the most. Okay, and I can show you a nice example in 3D now where I think they do this, and I think it makes a little bit of sense. So here is some three-dimensional data that is being shown to you in this nice animation. Hopefully, if this goes around enough, you can see this kind of like an oxygen atom or something. It's got three clusters, right? There's one down here, one here, and one here. And really what makes this problem hard is that there are three clusters, but the three clusters are not nicely aligned with the x, y, and the z axis. So you have these three clusters, but if you don't have a nice 3D animation, what you really look at in the x, y, and z axes are three kind of blurs like this, right? So the x values, a lot of them are near 0, some of them are a little bit over there. The y values are like this, the z values are like this. If you were just looking at the x, y, and the z, it would be hard to see that there are actually three things. But when you go to the principal components, it will change the directions, and they look like this. So this is, if I hit show PCA, it should do it for us. It'll look like this. So in the most direction in which there's the most variation is this direction of the molecule, the long direction of the molecule, and you can see that over here, PC1, the long direction of the molecule is now the aligned direction. That's the direction that spreads the data out the most. And a lot of interesting stuff is already in PC1, right? You can see the three clusters. There's something on the left, there's something in the middle, there's something on the right. It's nicely spread out. Now, here's where I want you to think. If we remove this long direction, now the data is like a two-dimensional data set of how far away you are, just either up and down, or into the board or out of the board, away from that long direction. So you have to use your imagination a little bit here, and imagine taking these three grapes and kind of having a long direction like that. And then if you remove that direction, every little piece is either a little bit above or a little bit to the right of each one. And the next principal component direction is saying, of that two-dimensional data set, let's do the principal component game again. In what direction are they varying the most? And in this situation, it seems like everything, except for this long direction, is sort of varying sort of evenly in all the other two directions. You can't see a lot in PC2 or PC3, which is telling you that most of the data is in PC1. There you go. Okay, so that's a nice three-dimensional picture of principal components, and you can start to see some of its uses. Okay, maybe I'll say one more thing in a second, but this is a good place to pause for questions or comments. Is the kind of idea of this, you do principal components on the leftovers over and over again until you get all the directions. Okay, let me say one more thing, which is as you are doing this, there is a notion of the how much variance does each PC capture. Okay, and this is going to be a Pythagoras formula, like we've seen a number of times. The total variance of the data, this is how much it's varying in total in all the directions. You can write this as the variance in PC1 plus the variance in PC2 plus the variance in PC3 and so on. Okay, and we chose PC1 to be the direction that maximized how spread out they were. So this will be the largest of all these numbers. This will be the larger. These kind of go in order. The variance of PC1 is bigger than the variance of PC2, which is bigger than the variance of PC3, and so on. But you can talk about what fraction of the total variance is in each of these things. So for example, it could be that PC1 contains 90% of the variance. Example, if the variance of PC1 is 90% of the total variance, then it says almost all of the variation is coming in the first component. If you know the first component, you know 90% of how the data is spread out. And the rest of the components altogether, they only contribute 10%. In a different example, you might say the variance of PC1, that could be equal to 30% of the variance of the total. And the variance of PC2 could be 20%. Could be 20% of total, and so on. And in this situation, they're kind of evenly spread out. So in the first situation, the data is essentially one-dimensional, which maybe I can write that down. Data is mostly one-dimensional 1D, in that most of the variance, most of how the data points are different is captured in one direction, but in the second example, it's a mixture, and you cannot just simply say it's one-dimensional. So it's some kind of thing. Of course, in real life, it's always some fuzzy mixture between these, but this can tell you how much or how little, how many principal components you want. You can keep adding principal components until you've captured most of the variation, and sometimes you'll have to do a few, sometimes you'll have to do very many. Okay, so this is multiple things. Okay, there's a few more examples on this page. I'm going to show you a few more examples as the class goes on. Most of this class is going to be just lots of nice examples with PCA. But once again, it was a great question, great place to stop for questions about what these things are in any of these examples so far. Questions? Okay. Let me ask you a question then. I've shown you basically what this is. You have some nice pictures, kind of transforming the data from one original basis to another. What is this useful for? Why would we do such a thing? And I've mentioned this a few times. And now my computer's frozen? No, okay. Let's go back to Mathematize. And let's go to what kind of tasks could this be useful for? Which of these tasks can dimension reduction, e.g. by using PCA, help with? Select all the ones that you think this might be helpful for. Okay. All right, let's pause this before it beeps at us. Again. Reveal. Okay. So 19 people voted. 15 people said compression. Compression is absolutely right. So compression means take the data and store it in a lower memory format. So compression. Take data and store in lower memory. And you can do that. How can you do that with PCA? How can this be achieved with PCA? How can this be achieved? Okay, what is the secret? I mean, we've kind of already said what it is, but let's explicitly, how would you achieve compression with this PCA technique? What would you do? How do you compress the data? Yeah. Please. Yeah. That's right. So I mean, I think you said it the nice positive way, the cup half full way. Keep as much as you want. I would say it the negative way, which is you delete whatever you don't want, right? But of course, these are equivalent. But you can either think about it as keep only the PCs you need, So instead of keeping every single principal component, you just keep enough to get the data that you need. Or another way to think about it equivalently, you could delete the lowest PCs, and that is this deleting is what makes it compression. If you kept everything, it would of course take up the same amount of space. But if you keep only a few principal components, then you are reducing how much memory you need because you've deleted all the other ones. How many should you do? It depends on what level of the compression you need. One of my favorite examples of this is this little example over here of doing it with pictures of faces. So these are pictures of different famous people and their faces. And you can imagine storing a picture, maybe there's a way we can compress it so we don't need as high of a dimension. And we'll talk about why you'd want to do this in some of the other examples as well. But you can think of, we have this picture, it's like thousands of pixels big. How could we compress that into less pixels or less memory? And here is a diagram of all these different faces on the first two principal components. And there's not a huge amount of help over here. I guess these people are facing right, and they're like the pictures are darker. Over here they're facing left, and they're lighter. But it does turn out, so 2 dimensions is not really enough to see what's going on. But if you look at the graph of, this is exactly what I was talking to you about a moment ago. This is the number of components you keep and the cumulative explained variance. So if you only keep one vector, that's only 20% of the total variance of the pictures. But if you keep, say, 80 components, then you have 90% of the explained variance. So in other words, 90% of what makes people's pictures look different can be explained with only 80 numbers, right? If you have 80 numbers, how much the PC1 is, how much the PC2 is, how much all the way up to the PC80, that will explain 90% of the difference between people's faces. So even though there's thousands and thousands of pixels, you can basically boil down somebody's face to an 80 dimensional number. And there's some nice examples of this. So actually I had a student who was my master's student who did this as a project at one point. So I'm going to show you his project if I can pull it out. Yeah, here it is. So this is exactly this data set. Image compression, a higher dimensional example. And so he loaded in these faces. Each face is, there's 1,560 matrices. Three-dimensional. What is the dimension of? Okay, here's the picture. At least 50 pictures each. Okay, but here's what I'm looking for. 50 times 37 pixels is the size of each picture. And so here are some of the pictures that they loaded. This is George Bush, kind of a low resolution picture, but you get the idea. And now if you apply PCA on these, you get these are the principal components. So this is the most important component of somebody's face is how much they look like this face. If they look a lot like this face, well, this explains 20% of the variance. So how much you look like this face, the projection onto this face is 20% of the variance. This one is 14% of the variance, and so on. Maybe I can make that a little bit bigger so people can read it. So there we go. This one is 7%, this one is 5%, and so on. And these are called the eigenfaces because they come out of this eigenvalue, eigenfunction, eigenvector decomposition. So some people call these eigenfaces. And what is the point of this whole compression thing is that somebody's face can be pretty well represented by a linear combination of these eigenfaces. And there's a nice example over here. So these are, by the way, these are the eigenfaces 91 to 100. These ones don't have much explaining power. They're kind of all over the place. Whereas these ones kind of do look like people's faces. So these ones are more to real life. This is kind of the signal that we want to keep, is how much facey people look like. And this is kind of the noise. This is like the higher ones, the really high principal components don't have much information in them. And you can tell they don't have much information in them because they only explain a very, very, very small fraction of the total variance. Well, in any case, you can do these projections. So here is somebody's actual picture. All right. And here is what they look like if you project them onto some lower dimensional space. So this is thousands of dimensions, right? What is the dimension of this space, of this picture? It is 37 by 50, so over 1,000 dimensions. And this is a 100-dimensional picture. This is, we now have an image which is an approximation of the original image, but lives in a much lower dimensional space. We've included only 100 directions. And the point is this is compression because instead of doing thousands of numbers, storing thousands of numbers in our computer, we can only store 100 numbers. So this is like a 10% compression, but the picture still looks pretty good. And that's because we didn't just do a random 10%, we did the top 10% directions that really explain most of the variance. There's another example over here. This is some other guy, Colin Powell. And again, this is the original image, that's the projected image. And they both look pretty similar. So you can project things down in a lot of situations as long as the first few components, if they explain most of the variation, then you only need those. So that is compression. Okay. Any questions or comments about compression? We're going to see more examples soon, other things you can do. But compression absolutely is one, and this is kind of a classical way to think about it. Okay, let's move on to what was the next most common thing people said. By the way, this was all on a post of what is the point of linear algebra? What are the real-life examples of using eigenvectors and eigenvalues? So in math programs, you take a lot of linear algebra, and doing linear algebra can feel like eating your vegetables. You're like, why are we doing all this? But this is why. Okay. All right. Compression. Next up is clustering. Clustering, absolutely classical thing as well. We have seen all the examples that I've done so far have kind of been with clustering. That was the 4 countries. 3 of them were in one cluster. 1 of them is in another cluster. And so if you have something complicated, you can cluster it into pieces in the principal components and kind of see the clear difference. I have one example that I will go into soon, and we are going to be spending more time with later, that I really like. And again, the input space is images. This is from a book on the mathematics of machine learning. The input images are images. They are the MNIST images that I talked about way back in September. And I'm looking at the images that are zeros and the images that are ones. And if you take the principal components of all these images, so each image is a vector in like 700 dimensional space, which is really hard, really big. If you project it down to its top two, just two principal components, out of 700 dimensions, we only kept two. You can already see a very clear difference between the ones and the zeros. So the ones are over here, and the zeros are over there. And you can see like a clear difference. The ones are on this side, the zeros are on that side. So you can kind of cluster things. Even if they're hard to tell apart in the original space, they might be very easy to tell apart in the projected space. So this is another really nice application of PCA. Okay, clustering. What else we got? All right, so 15, 13, the next one. 12, classification tasks. So how would we use PCA for a classification task? Let's think. Classification tasks. How would PCA help? I think this is a great thing to think about and kind of relates to a lot of themes we've talked about in the course already. So first of all, in what way would we use PCA, and in what way would it help? Anyone want to think for a minute on either of these? Yeah.
So dimension reduction, so maybe some methods like cable can help to reduce dimensions or make sure.
Yes, I think you've already assumed the first step in your head in your answer. But what is like the first step? Like how would you go to the computer, you're like, I want to use PCA and a classification task. What do you do? Calculate the variance. Well, so sort of the PCA is a funny way of calculating the variance, right? The variance in your data, if you do PCA on it, you've sort of split the variance up into pieces, right? There's the variance from the PC1, the variance from the PC2, and they all add together to give you the original variance. But how does this help you? How does this help you tell things apart, right? That's fundamentally what classification is. So you're all on the right track. Anyone else have an idea?
It's more easier to see in the lower dimension, higher dimension you can how it is like in the second dimension, 2 dimension or like 1 dimension. It just okay from here to here, the one category to.
Yes. Okay. I think this is like the fundamental paradox we talked about way back in the beginning of the course. Is that sometimes when you have more things, you think more is more helpful, but actually more can be harder, right? More dimensions can make the classification task harder, and in particular, if there's lots of dimensions that are actually useless, right? If that's adding a lot of noise to the data. So we've seen this in a number of different ways. And so how does PCA help? It reduces the amount of noise, it reduces the dimension, so you can reduce the dimension or noise, however you want to think about it. And therefore, when you apply a method to it, if you apply it after you've reduced the dimension and the noise, it will have lower variance as well. So reduce dimension or noise. Therefore, apply any method after PCA, and I'm going to say might, because it doesn't always work, right? Might work better. So just like you saw in Project 1, like less features can be better than more features, right? Having too many features can actually be a problem. And the PCA is a great way to sort of figure out which ones matter and don't matter, and then you can delete them sort of explicitly over here. So you can imagine, for example, if I said, please write, let me go back to that example that I had a moment ago, right? If I said, please figure out these 700 dimensional images of zeros and ones. And okay, if you haven't taken a data science course, you say 700 dimensions, that's great, we have so much data to work with, right? But actually, you're wrong. 700 dimensions means there's a lot of dimensions that you will overfit on. So if you try to work with the 700 dimensional data, you have so many different things. Every individual pixel sort of doesn't really matter a lot on its own. You're going to have a really hard time with it because of overfitting. And you're going to overfit these 700 dimensional data, and it's going to be quite hard. But if you could reduce down from 700 dimensions down to 2 dimensions, and look at how nicely spread out it is, then your classifier is going to have a lot better of a time. So you can, by reducing the dimensions, you are reducing the amount of noise, you're getting rid of things that don't matter, and keeping only the things that tell you apart, the ones and the zeros, right? These are the directions where the things are the most spread out. And that is exactly what your classifier should be looking at. So it's sort of an automatic way to choose features, and that's how it goes with classification. So automatic way. You can also think about it this way. Automatic, good way to choose features, right? So it can replace a lot of these other things. Okay, why do I have these words? I have might starred, and I have good in quotes, right? And we're going to see that it doesn't always work, right? So PCA is not this like magical wand. You just like do it and it'll always work. Sometimes it works amazingly well. So for images, for example, it can work really well. But you need to be careful because it doesn't always work. So it's not like a magic wand that definitely will solve your problem, but it can make it a lot better or a lot easier. And you do have to combine it with all the other things we've learned in the course. So it really is just a way of going from 784 dimensions down to 2 dimensions, and then you can apply anything we've learned, and it will work better. I will say there is one in particular. Yeah, maybe I'll do the question first. Yeah.
Sorry, I was just going to say, so when you say it might be better, does that mean it could be worse or just sort of be close?
I think if you kept all the components, then it will be the same, or it won't be worse than the same. If you keep less than all the components, you have deleted some stuff. And basically, it's a good method when the stuff you delete is like more noise than signal, and it's a bad method when the stuff you delete is more signal than noise. So if you look at the principal components, and it happens that a lot of what you want to capture is captured in a small number of principal components, then it's a great method. And sometimes you look at your data, and what you actually want to capture is spread out over many, many principal components, and then it's not as good of a method. And it just depends on your data. Will your data be the kind where there's a couple directions that tell you most of what's going on, or is your data the kind of where it's all spread out? And yeah, this is a great example where it is nice down to 2 dimensions. And we're going to see like more and more advanced ways in the next week of getting this to work. So yeah, in fact, I would say this is like the core of how like ChatGPT works. It's fundamentally something like this. We'll talk about that Wednesday and Monday. So even things that seems like it might not work, you can often force it to work. Yeah, great question though. Yes, and in practice, you just have to try it and see. Like I don't think there's a way you can like theory craft ahead of time. Will it work or not? You just try it, you see if it works, and then you go from there. Okay, yeah, great question. Anyone else? Yeah.
Does it work worse on correlated data set because if you delete the noise, the data is...
Yes, okay, that's an absolutely great thing. I think it works extremely well on correlated data. And you can see that in the picture that we started with. Let me see if I can pull up that picture, which is here. Where's my picture? We can go back to this one. So right, this data is highly, highly correlated, right? Correlated means when the x increases, the y increases with it. So highly correlated data is a problem in the original space, but when you move to the PC space, your PC space is automatically finding directions where they go together. So in this particular example, it's highly correlated, and you can see that, yeah, there's one direction where the correlation is going. That's the principal component 1. So in some sense, it is really explicitly pulling out the correlations. It's pulling out the way in which things vary together as the principal components. So it's very good for highly correlated data. Yeah, great question. Anyone else? Okay, so where are we? We've written it's good for classification because it can automatically pull out things. It can sort of detect correlations. So somehow detecting correlations is built into the structure of maximizing. Okay, that's classification. What about, oh yeah, there was one other thing I want to write. There's one particular method that we talked about in this course that really relies on the variables. So one classification method relies on the variables a lot, and that is trees. And the reason is that trees are defined to look at one variable at a time. So a tree will ask a question like, is x1 greater than 7, right? Like this is the kind of thing a tree will ask. And then it will then go, is x2 greater than 3, right? And then it'll say like yes or no, and so on. And the point is, in our definition of a tree, every individual question has to be about one variable at a time. And because of this, the trees, they must kind of respect the variables that you give it. If you give a data set to a tree method, it will automatically, because of the definition of the trees, it is looking at every individual thing on its own. If you do principal components first, then it can ask questions. So this is a tree before any manipulation. Okay, but if you do a tree after principal components, so in other words, if you do the principal component transformation and then apply the tree method, actually the types of questions you get, even though they seem similar, are going to be totally different. Because the questions will be of the form, is principal component number 1 greater than 7? Okay? And this is the big important difference. Before, we could only ask about every individual variable. And now we can ask about the principal components. And the principal components have a combination of all the variables in a smart way, right? So like a great example, going back to what this thing is, if I can only ask about the x's and the y's, it's hard to figure out these different things, right? Like for example, if I want to say, let's say I want to figure out if you're above the line or below the line, right? This is a great example. It's really hard to tell which of these are a little bit above and which of them are a little bit below. Like I would like to draw a diagonal line and say above or below. And in the original space, if I can only ask about x and y, it's like impossibly difficult to do that. So I say if the x is large, then I'm going to capture both above and below the line. If I say is the y small, then I capture both above and below. But over here, I just ask is PC2 bigger than 0 or less than 0, and it's automatically capturing that. So the point is that the tree method, after principal components, can ask a totally different set of questions than before principal components, and sometimes that is useful. So this is a particularly good combo to keep in mind. Okay, so that's one thing I wanted to mention. Yeah, on the other hand, there's some methods, like if you're doing linear regression, then the types of questions you can ask in either space are technically the same. But for trees, it's totally different. Okay, so that is, I think, all I wanted to say. So this might be a great question to ask. Okay, let's put et cetera. And then so this, potentially very good, potentially strong. Okay, so that is classification. Going back over here to what you guys said, and I accidentally just open this again. Let me. Huh? Now they're gone. Okay, I need to find the window. All right. So we've done compression. That was correct. Clustering. That was correct. Classification. That was correct. What is left is visualization and regression, which were selected by about half the class, right? 19 people, and we had 11 people choose them. Visualization, this is an absolute classical thing. A lot of papers you read in biology and so on, they will just say, here is a graph of our data in the PC direction. And the reason is because paper is two-dimensional. When you try to make a two-dimensional plot of any amount of data in higher than 2 dimensionals, the PC is a really good way to do it. There's other more complicated things that you can do to visualize, but principal components is a great way to make your data fit on 2-dimensional paper, and so it is used all the time. This is like a very classical thing to do. Okay, last but not least, the one that was voted on the least is the one called regression tasks. And this word I think is confusing. I think this is why not many people voted for it. Let me remind you what a regression task is. And the problem is the word regression is overloaded. So regression, as a word, it can mean linear regression, right? And that is kind of referring to this formula, y equals beta 0 plus beta 1 x1 plus dot, dot, dot. That's linear regression. That's like a model. But it can also mean the type of problem where we are estimating a quantity, type of problem where we estimate a real number. So if you want to estimate the price of a house, that is a regression task. If you estimate a price of a house with linear regression, that is like double regression, regression. And so sort of the word regression gets used to mean two different things. And if you thought I meant linear regression, so you could do linear regression with the principal components, that is something you could do. But I was talking about this one. I was saying a type of problem where you estimate a real number. So it kind of fits into the same. You can say regression versus classification, and classification is where you estimate a class, right? Estimate a discrete class. Versus regression is you estimate a real number. And principal components is totally legit for this. So also good for this. And again, you can combo it with any method. So can combo any method. Combo. So you do PCA first, and then do any regression method. Okay, and a really great example is if you did PCA first and then you did like forward subset selection, it would automatically find what is the best number of principal components to keep, right? So you could kind of by hand say, oh, let's try it with one or we'll try it with two. But you could say, just transform the data into the PC direction, in the PC directions, then do the subset selection, and it'll automatically go through and do them. You could even try them in order, right? So this is one of the things that made subset selection slow, was that it was trying every single combination. It was trying like n squared things. But if you do them in order, if they're the principal component directions, it makes sense to do them in order. They are in an order. And then you can try only n things. So you can combo this in a number of ways. And so it absolutely works. So what was the answer on the mathematize is all of these things are working quite well. So all of them are good. They're all valid things to do. Okay, any questions or comments about these applications that I've said so far? Okay, so I've sort of been like building up principal components. I'm like, oh, it's good for this, it's good for that. It is a really great tool to have. It has a couple downsides that I want to talk about now. So here is a disadvantage. What is a disadvantage of PCA is that you lose the blank of the variables. And there are a number of things you can put in the blanks, but I want you to think carefully. What could you put there that would make this a true statement? Okay, I'll give you a few minutes. This is the disadvantage of the PCA is that you lose the blank of the variables. What is the blank? And there's many, many possible answers. Let's see. Meanings, interpretation. That is interpretability. This is very, very nice. This is absolutely correct. What did I write? I wrote something like that. Look at all these. I guess I left everything as correct. But yeah, the right answer is when you move to the PCA space, this is like a warning. 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 So the PC directions are weird linear combinations of the things. PC directions are weird linear combinations of the original directions, original components. So even if the components had nice meanings originally, once you switch to the PC, then you have to give up having meanings to them. A good example is the very first thing we did with the countries. Let's see if I can find the countries once again. Okay, let's see. I can just go to this little, this is this, this is this, and this is the first example. So, right, our original data set, we say like, this one, like the reason this country is different is because they have less fresh fruit. Like that was a thing you could say. Once you switch to the principal component direction, so it's a lot easier to determine that Northern Ireland is different than the others. But if someone asks, what about Northern Ireland is different, right? Well, you say, oh, well, if you add up 0.1 times sugars minus 0.7 times soft drinks plus 0.3 times processed veg, then you get a bigger number than like these other guys. So it doesn't mean anything anymore. It's hard to explain sort of why this happens. I mean, I guess you would have to go in and analyze what's going on. So you lose the interpretation that you could get from the original data. So you don't always, if you want to have that, then you should keep the original data. Another good example of this is going back to something I already said, right, is if you do tree-based methods, right, the tree-based methods originally are only looking at individual variables, and then afterwards, they are looking at the principal components. And I said this could be a lot better. This could be more performant. It could automatically find patterns. But, you know, part of the reason trees were nice is because these questions were questions about things we can measure. So if you're a doctor and you're like, is this person having a heart attack? I can check. Is their blood pressure greater than a certain amount? Is there, is their temperature greater than a certain amount. Like these are all questions that make sense. Whereas if it was a principal component, it'd be like, measure their blood pressure, multiply it by 0.7, add it to their temperature times 0.3. Then like, you'd do some weird combination of all the variables that doesn't really make any interpretable sense anymore. So you lose the interpretability. So this is the warning of principal components. Are weird, so you lose interpretability. Therefore, lose okay. So that is something to watch out for. And there's one other thing that is interesting with principal components, or PCA, that I will now ask you about. So very nice people figured that out. Here is an example data set. And I have some training data and some testing data. The data has two features. So it's in 2 dimensions. And I want you to kind of visualize what would happen if we applied PCA to these data points. Principal component directions are trained on the training data on the left, and then they are used to try to do a classifier for the training data on the right. So we do principal components to try to remap this space and then try to help us out. We plot the data in PCA space. Does the PCA space help us figure out the two classes apart? Does it help us figure that out? This is a perfect thing. We'll start off on next class. I will rejig this so that the green points match our system. We'll be all in a circle, and then we will twist the line around and see what the PCA comes out with. Okay, so I'm going to make the data set in this picture. We're going to redo what we did last class with the PCA, and we're going to see what happens for this particular data set. And that will lead us into our next topic, which will be on neural networks and other more complicated things for the last few weeks of class. Okay, I think that's where we're going to stop. So we're going to stop a little bit early so I can make this example for you guys next class. Yeah, that's where we'll finish for today. Any questions or comments before we go? Okay, great. Don't forget to